done 2 example problems involving Newton's law of gravitation so far. Example number 6, where we had 2 people a certain distance apart, and we found the force of gravity that acted between the 2 of them. We also did example number 7, where we had a person a certain distance away from the Earth, and we wanted to find the force of gravity between those 2 objects, the Earth and the person. What do they have in common? We're trying to find the force of gravity between 2 objects with mass. If we take a look at number 8, this one's different because we're trying to find the force of gravity involving 3 objects here. This question says find the net force of gravity acting on object number 2. The inference is that we have a force of number 1 acting on number 2, and we have a force of number 3 acting on 2. And we want to find the net force, the combined force of 1 on 2 and 3 on 2. So here's how we tackle this. It goes back to our dynamics unit. When we have 2 forces acting on 1 object, we'll draw a free body diagram. Let's pretend number 3 doesn't exist for a second. Look at number 1 and number 2. There's a force of gravity between number 1 and number 2. It's an attractive force. That means 1 is pulled towards number 2, and 2 is pulled towards number 1. But since we're trying to find the net force that's acting on number 2, I don't care about the force that's acting on number 1. There is a force there. It's equal and opposite to the force acting on object number 2. But I don't care about that force because I'm looking for the net force on number 2 only. Now let's pretend number 1 isn't there. Let's pretend just 2 and 3 exist. 2 and 3 attract each other, just like in the last 2 example questions. 2 is pulled towards number 3, and 3 is pulled towards number 2. But I don't care about the force on number 3 because that's not the question. We're looking for the net force on number 2. So we're going to find the force caused by number 1 on number 2. We're going to find the force of number 3 on number 2. And we're going to combine those 2 forces to find the net force. So let's define those individual forces now. Let's find F1. F1 is the force that number 2 is pulled towards number 1 with. F1 is equal to G M1 M2 over R squared. That's 6.67 times 10 to the minus 11 times 10 kilograms, that's mass number 1, times 20 kilograms, that's mass number 2, and we're going to divide that by the distance, 5.00 meters squared. We do our math there. We end up getting a value of 5.336 times 10 to the negative 10 newtons. Try that on your calculators and make sure you can get that number. Now let's find the force of 3 acting on number 2. Both of these forces, F1 causes F2 to be pulled towards number 1, therefore to the left, and number 3 causes number 2 to be pulled towards number 3, to the right. So we're going to say F3 is GM2M3, the force of gravity between 2 and 3, divided by R squared. That's going to be 6.67 times 10 to the minus 11 times 20 kilograms times 30 kilograms, divided by, and the distance here that separates these 2 objects is 4 squared. We do the math on our calculator there. Make sure you can get this answer, 2.50125 times 10 to the minus 9 newtons. Now, what do we do with these 2 forces? Same thing as we do with any other 2 forces. We want to combine them. Any other free body diagram, we say F net is equal to the sum of the forces F1 plus F3. Now, usually at this stage, we also say F net is equal to M times A, or recently we've said F is equal to mv squared over R. Here, since we're just looking for the net force, we'll just leave it as F net. We're going to say F1 is 5.336 times 10 to the negative 10. F3 is 2.50125 times 10 to the negative 9. What are we missing here? Well, we have a free body diagram that shows that object number 1 pulls on object number 2 to the left. So I'm going to make this force here, the force of number 1 on number 2, a negative value. We're going to keep the force of 3 on 2 a positive value because it's acting to the right. Let's add these up. When we do, we get a value of 1.97 times 10 to the negative 9 newtons. There's our net force. That's a positive value, by the way, which means the net force is to the right. In other words, F3 is bigger than F1, and you can see that by the numbers that we found there when we calculated those two forces. Let's take a look at number 9 as well. It's a little bit different than number 8, but not entirely different. We have 3 objects here that we want to find a force of gravity between as well. This one says find the net force of gravity acting on object number 2. We're going to start off the same way. We're going to look at 1 and 2, say they attract each other. 1 is pulled towards number 2. 2 is pulled towards number 1. But I don't care about this force because I'm not trying to find the force on 1. I'm trying to find the force on number 2. So I care that 2 is pulled towards object number 1. Now let's look at 3 and 2. 2 is pulled towards number 3. It's attracted towards number 3. Now 3 is also pulled towards number 2, but I don't care what happens to number 3 because I'm not looking for the force on number 3. I'm looking for the force on number 2. I care that 2 is pulled down towards number 1 and that 2 is pulled to the right towards number 3. So let's find the force caused by number 1. Let's find the force caused by number 3. And then let's combine those. Let's say F1 is equal to G M1 M2 over R squared, 6.67, times M1 is 30 kilograms, times M2 is 90 kilograms, and we divide that by R squared, 60 meters squared. You get a force there caused by number 1 on number 2 of 5.0025 times 10 to the minus 11. Make sure you can get that number on your calculators. Now the force on number 1 would also be 5.0025. It's equal and opposite to the force on number 2. But remember what we said, we don't care about the force on number 1 because that's not the question. Let's find the force caused by number 3 on number 2 now. We're going to say G times M2 M3 over R squared. That's 6.67 times 10 to the minus 11 times 90 kilograms times 75 kilograms divided by the distance squared, which is 80 squared. Calculate that value. Make sure, again, you can get this on your calculator. I get 7.03477 times 10 to the minus 11 newtons. Now I've got both forces acting on object number 2. We got to combine them. How do we combine these? Yeah, we know how to do this. We got to add these forces together, but because they're in 2 dimensions, we say they're non-collinear vectors. We have to add them vectorially. 7.03477 times 10 to the minus 11 to the right, and 5.0025 times 10 to the negative 11 down. Vector diagram drawn head to tail with the resultant vector drawn start to finish. And where are we going to label our angle? Position 1, 2, or 3. Yeah, we always draw that resultant vector at the start of the vector diagram, which is be position 3 here. So we're going to find F, same ways we found it, same ways we found displacement in those problems in Unit 1, same ways we found the net force in Unit 2 with a 2-dimensional problem. We're going to do the Pythagorean theorem. We're going to say 7.03477 times 10 to the minus 11 squared plus 5.0025 times 10 to the minus 11 squared. Let's put another set of brackets around that when we do our square root. When we calculate that value, make sure that you can get this on your calculator. I get 8.6 to 2 digits. I get 8.6 times 10 to the negative 11 newtons. And because force is a vector, I need direction. This is an angled direction, so let's do the inverse tan function of opposite over adjacent. That's 5.0025 times 10 to the minus 11 over 7.03477 times 10 to the minus 11. Theta works out to be 35 to 2 digits, 35 degrees. And we'll say south of east here. We'll say that. If you had drawn the blue vector first and then the green vector, you would have gotten 55 degrees east of south. Same answer though, 8.6 times 10 to the minus 11 newtons at 35 south of east, or 8.6 times 10 to the negative 11 newtons at 55 east of south.